Yeah, put in that Stevie chat. All right, guys, it is 10:30. We're going to get started. I'm Sean. You guys don't know, this is Eli. Back there, we have our two other sub-leads. We got Kylan and Anjana. Eli is the power sub-lead, Kylan is the control sub-lead, and Anjana is the data acquisition sub-lead. For the senior design project, we actually split into 4 groups. So we have power, we have sensors, control, and software. The data acquisition team split into 2 teams, one doing sensors and one doing the software. We also pulled 1 person from power, 1 person from control, and those people are helping on the sensor team as well, but they'll be working a lot more with their respective groups. So here we have a basic block diagram of how the system's going to work. So starting from solar here, you got solar, charge controller, batteries, power distribution unit, which is essentially going to give us some stable DC voltages for things like sensors, control boards, stuff like that. So it's going to be a lot of power electronics. That's one of our more complex things that we're building this year. From there, we're going to be piping that into our control. So control is going to be handling a lot of the, obviously, well, we have control loops, which are going to take a lot of tuning. We have a bunch of safety systems. We need relays to switch stuff over. That's going to go into the all tracks, and this is going to be kind of a more group thing. So power is going to work with control in order to get really good efficiency out of the motors, because we're going to have to do unloaded testing and loaded testing and figure out our throttle curves for those. And since we're separating motors this year, we need to make sure that the RPMs are matching. So that's also going to be part of sensor's job, is modifying the throttle input so that we have motors that are running at the same RPM. Finally, that goes to the motors. We have 2 8-kilowatt motors. I believe they're about 104 RPM per volt. I think is what they're rated for. Yeah. So I think we get 3,600 RPM. I think we're doing direct drive or shaft down on the bottom of the boat. No gearing or anything. So currently the motors are driving a common shaft. They are permanent magnet, and part of the reason we need to take those apart is if the poles in a permanent magnet motor aren't completely aligned, you actually get feedback and you get crazy efficiency losses. You get like a ton of whining. We got weird stuff with the motor starting and stopping. It wasn't good. So we're pulling those apart this year. This schematic is actually for the senior design project. So some of the stuff isn't exactly the same as it will be on the club side. I will release a version once we're done here today that is 1 for the club and 2 for the senior project, so that you can see where people kind of lie. We are going to have a lot of sensors on this boat. We need a lot of telemetry. So we have to know things like tilt. We have to know like what power we're drawing. We have to know what RPM we're running at, what position our rudder is. So sensors is going to handle all that. They're also responsible for all the sensor code. So getting the sensors into the devices. We also have the rudder, so it's going to be responsible to control. But we will have a sensor on board to detect the rudder position, so that if anything goes wrong, we're getting some feedback from it. What's happening. That's all coming over into the Raspberry Pi. So the Raspberry Pi is actually purely supervisory for this control system. I think we're going to end up going with UART. I have to reread the document that I was sent by one of the team members, but I think UART is probably the best form of communication, because it doesn't allow the Raspberry Pi to write to that STM board, and we just want to grab all the sensor data off of this. So from there, we're actually going to have a display. So I believe the one that we're looking at right now is, I think it's 1920 by 1200. It's 12 inches and 1,000 nits peak brightness. So that way we can see it, in the sun, since the boat's going to be running all day. So that means we're going to need a GUI. So we're going to have, digital gauges, just like you'd see in a car, displaying all the critical information for the boat. And we're actually going to replicate that in a server. We also want to host files with that so that we can download our data logs. I believe Eli wanted to figure out kind of who wanted to be in what team.
Oh yeah. So I know our seniors and people have teams. Your teams also like if you're sensors, I know you fall on the data acquisition. So for everyone else, I know we have power people, I know we have control, thank you, and data. So for format power people, just across the board, senior design ads, right? What do you mean by it?
I'm new. This is my first time coming.
Oh, perfect. Okay. You figure out again. Take 7. Control. Who's control is in
That's a lot of people that can make it. It's all the people who work on Saturdays. So.
Okay. So for you four, your job's gonna be a little bit harder. My apologies. We'll try to figure out a way to streamline that. And then lastly, data up to the rest of you guys do that. Start with your hand. Please do. This doesn't look good at all. It's like half of my viewers.
The hand up there.
It's like a big $7.
Yeah, I think so.
Okay, thanks.
So so for people who are new to the club and not on the senior design project, when we do assign you stuff, you'll be working with some senior design project people to figure out things, do design, testing, all that stuff, just because we need to have a hand in everything that is going on here. We'll have no shortage of projects at all. We have 17 people, like I said, in the first meeting 2 Saturdays ago. 17 people in our senior design project. So it's quite a big task. We're doing all of this as part of one big senior project that at the end of the year, we're putting, all of our documentation, everything together for, big presentation. So it's going to be really cool. Move on to power.
Oh, yeah, if we want to talk about just directly power. Alright, so for my power people, I'm sorry, I will surprise all of you because we made it So first off, our power statement. So of course we have a power statement. Power statement exists. Obviously, the power statement is going to be all together. So obviously the power statement is going to be the combination of everything. You know how this big chart exists? Basically we're going to do this, but for power. So what's going to happen is we're going to separate into a solar team that directly handles the charging controller. We're going to separate to a battery team. The battery team is going to be all alone and sad and unhappy. That's okay. And then we have our power distribution unit team. So the team that's doing PDU is going to be broken down into 2 parts. They're going to be auxiliary, and then they're going to be our main power. So the difference between our auxiliary and our main power is that for our main power, we're basically just boosting. We're bucking our system and boosting our system. So the first thing we're going to do is boost. The first thing we're going to do is boost the system. What that means is that we're raising our voltage from the standard 36 that we're getting out of the batteries up to 50 volts. Now, for anyone who's really confused on why we're doing that, completely understandable. We're trying to negate power losses. Not completely negate because that's not possible, but we're trying to reduce them by a lot. So what's going to happen is by boosting our voltage up to 50, we lose a lot of the I squared R losses that we get. So I squared R is just another power calculation. But the current is one of the big loss sources. So by boosting your voltage, you don't get that loss anymore. The auxiliary is not going to be about conserving resources. It's actually more about setting our voltages to do different inputs. So as you guys know, we are directly working with control and data, but data less so, and those need different voltages. So for a lot of our sensors, it's going to be 3.3, 5, and 12 volts. That's 3 different voltages, and our system only outputs 1, and that's 12 volts. So the second power distribution unit team is going to figure out how to properly buck our system in a way so that it outputs to all 3. Now, the big thing with PDU is I don't want to just buy a bunch of components. If we buy a bunch of components, it makes our entire task useless, and we're not learning anything, we're not getting anything. Which means we get a really, really fun task of working with microelectronics. So we're working with MOSFETs, diodes, and other things like op-amps, all that. Resistors, MOS resistors, so one thing you all should know. It's going to be a lot of research, it's going to be a lot of building schematics throughout the spice, and then once we get all of the schematics, we're going to break them down into one box that has all of the components within it, and then that T-Spice file is going to be sent to our main spread that we're going to have. So moving on from our power and power distributed, I'm not going to say it right. moving on from that side, we're gonna go over to batteries. So for batteries, we're going to be doing two things. One, we need to cycle them and figure out what their efficiencies are, and making sure that they're balanced at pretty much all times. The other thing we're gonna be doing with our batteries is we're gonna be building them a battery box. So that is kind of mostly mechanical, but not anymore. Sorry, guys. Our goal with the battery box is to make our batteries modular. So with batteries, you can set them up in either series or parallel, right? Y'all should know this. What we want to do is be able to optimize our battery systems for the races. So in our endurance race, we're going to need them at 36 volts. We don't really have a choice there. But for sprint, we can actually bring it down to 24 and or smaller, whatever size. So the battery people's job is going to be figuring out what are the optimal battery values for each race, and then figuring out how we can easily switch between the different setups. That's what battery box is going to be. Figuring out how to go from series to parallel really easily all at once. What's up?
What's the sprint race voltage?
Sprint race? I don't know. I don't know how to
That's one that's gonna be testing.
So that is one thing with the batteries. You're gonna have to do a lot of testing. You're gonna have to figure it out. I'm also probably gonna have you guys working hand in hand a lot with solar because both of those tasks aren't the heaviest. But I might also just put you guys on the motor. Actually, no, I take that back. Batteries definitely gonna motor. So the other thing I'm gonna want you guys to do is there's gonna be a dyno. We have a dyno, and the dyno's gonna need to be tested. Now that dyno testing, not the dyno, the motors are gonna need to be tested. So the motors are tested through the dyno. You'll be working with the mechanical team directly with that. Not be too fast, let me know. But because they're working directly, you guys are gonna be gathering the data, finding the data, and figure out what that data means. So that's gonna be your other secondary job. Lastly, we have our solar team. Our solar team will you get a slightly easier job. So for solar panels, there's gonna be three main issues. One, our solar panels ideally would be 48 volts. The ones we're gonna get are about 20 volts per panel, which means when you add them together, it's only about 40 volts. Now you're not allowed to go over 52 volts in the system, which means we can't put them all in series, which make our lives so much easier. That means you're gonna have to figure out a way to boost it. Normally that would be the PDU's job, but they're boosting the internal circuit. So that means for our solar people, you're boosting the solar panels themselves. The other thing with solar panels is it's not an arbitrary value. You're not gonna get 40 volts straight. It's gonna fluctuate and change because you're getting it from the sun. And as you turn, as you make a little bit and all that, your voltages are going to change. So you have to find a way to stabilize that, set it away with the charge controller, but mess with the charge controller, and or getting a new charge controller. So that's something I have to look into, research. Along with that, we do have one charge controller now. The issue is it only bucks. So I don't think everyone over bucking, but bucking basically means it only drops our voltages to whatever value we want. If our panels are 40 and we're trying to get 48, we can't really get up to the 48 without boosting our system. So that means we may need a new charge controller, but funding, and or you figure out a better way to boost our voltages coming out. Along with that, you're also going to have to figure out the terminal setup. So of course, it'd probably ideally be series parallel. Two in series, both of those are parallel. But if you find an optimal system, want to go Y delta, please don't do that. Then you can. So have some freedom there. After that, you'll be working with batteries just to make sure all of your transfer goes well. And then you're going to be testing your panels to make sure they're actually running at their near 40-ish volts, figuring out what their current output is, and then figuring out how that discharge works. Along with that, we're going to do 3 different tests. There's one test that's basically directly testing the voltage. We have a flute for it. It'll test the voltage. If you guys read the manual, you should know how this works. But we'll test our voltage. It'll give us a current, and that allows us to see the power of the graph. That means it's also internally doing the power of the circuit as it goes through. We want to that's basically our MPPT tracking, maximum power point tracking. So with that, you'll know exactly how to optimize the panels. We're also going to try and get the Edison tester to basically verify your results. So those are the things we'll be doing for solar, battery, and PDU. Has any questions out for our article? Nope, perfect. So at some point today, we're going to break down into those teams for everything.
All right, so I just want to go over, kind of summarize what Eli's saying, so that everybody knows what voltages we're getting, and how everything's connected. So coming over solar panels, we need it to be 48 volts. So we're gonna have to boost it. We may also, Eric.
Yep.
So we are gonna have to boost it to 48 volts. So we need 48 volts going through our charge controller. Can you set this up on Discord instead and do
Oh, gotcha.
do a CS recording?
Okay.
Thank you. So, like I said, we need 48 volts going into our charge controller. Our motors are rated for 36, so we're going to keep the voltage up at near 50. until right before our motors, and then we're gonna buck it down to 36 and get really stable voltage out of it. We don't want a lot of ripple because that causes fluctuation, feedback, a lot of noise, power losses in the motor. So right before the motor, we put it back to 36 and keep that stable throughout. We haven't fully decided on the battery voltage that we're going to have yet. We might have 24 volts on that just because we need to keep stuff at 12 volts. But we're allowed to take those batteries out and charge them using wall power. So there's nothing that we need to do special there to like maximize, our battery charges or anything like that. We just have to make sure that over the course of an endurance race that we're able to keep our system. 2 endurance races? 2 hours. Well, yeah, 2 endurance races, but it's 2 hours. About 2 hours. We need to make sure that our batteries can last that long and then some while powering all of our systems, doing the most intense tasks, because then when we're doing the lighter stuff, we can be sure that, hey, we're not going to die over the course of the race. So that goes to the PDU. So for control, specifically control and sensors, we actually need a few different voltages. We need 3.3 volts because our microcontroller, the STM32 G474RE and the Raspberry Pi Model 4B, those are 5 volt tolerant, meaning we can put 5 volts in, but I've seen a lot of stuff that says if you run the voltages at 5 volts for too long, it can kill those boards. So we want to keep it as close to 3.3 as possible, because that's what all the voltage sensing range is. It's all 0 to 3.3 volts. So the auxiliary PDU is going to handle that. We also need 5 volts for powering our things. And we also need a stable 12 volts. We do want to be able to live stream these races from the boat. So we need some way to keep devices charged for the duration of especially the endurance. That's the real big one that we're worried about running out of charge for. And then for the main PDU, that's going to handle keeping that 36 volt power to the motors clean and stable. For the battery team, we do want it to be modular. We're not fully finalized on the batteries that we want yet, but we have 2 requirements: 36 volts and 100 pounds. Oh, and I guess 3. We have sealed AGMs. We can't use LiPos. We can't use anything else. So it has to be sealed AGMs, marine grade, like normal car style batteries. So we need to maximize our power output coming out of our motors, and that's primarily going to be a responsibility of the power team. But like I said, the control team will assist because we will need to be converting voltages up and down for sensors and get that throttle in line. Anything else for power? So we will be compiling a finalized list of specifications, a way more detailed version of this block diagram.
At least for my power people, I kind of want everyone on it, but if not, we will be using Visio, so basically we're going to be making a block diagram, similar style, except it's going to get more specific, especially if we're getting more teams. So what kind of buttons you're using, how they're going to be wired, everything. So it's going to go from large scale like this, and it's going to get slowly broken down to a smaller scale. And everyone's going to need to be on it, update your block diagram, and then have it updated to everyone.
Yeah, so essentially what Eli's saying is that when we make these block diagrams, when we can you click through these block diagrams on Visio and go into the deeper version of it?
Several times.
So say for this PDU block diagram. So here we see the PDU on our general overview of the whole system architecture. But when we actually go into the PDU, we want to see, hey, we have the auxiliary part and we have the main part. And then once we go deeper, we have another box that's here's all our voltage steps, and we got an input and then all the outputs. But then we want to be able to see this specific circuit, right? So it might be like an op amp or whatever, something like that. We want to be able to go through and go deeper and deeper and deeper until we hit the circuit level. That just helps with abstracting it for, like, especially like, let's say I need someone from control to look at what power's doing. We want them to be able to take a glance at it and not really worry about what the actual circuit itself is doing. Just kind of know like how things are connected and what the outputs are going to look like. Because we're trying to build wiring harnesses. I think we're going to end up using Molex connectors for our sensors and low voltage stuff, and then for power, that's up to that guy right there. Don't talk to me about that. But yeah, we want to be able to take things apart. We want to be able to fix them, repair them, put them back together with not a lot of downtime. That was a big problem we had last year. Every time we needed to get to something underneath the solar panels, it was at least half an hour just to get the solar panels off, and another half an hour just to get the solar panels back on, not including the work that we had to do underneath. And we did, unfortunately, have a battery explode last year. Well, explode. It cracked and it was leaking battery acid. But we don't want stuff like that to take a long time to get out and put in the battery box. So that is something we'll also be working on. Questions, comments, concerns for power, ideas, anything you think I might have missed, anything you think Eli might have missed.
If not, you'll better have someone go on a smaller scale. Because if you've done research, you should kind of understand something.
If you don't understand, now's the time to ask questions. We are here to learn. We are here to answer them.
Yeah. Plus, if you ask a really good question that I also don't get, then we have something to figure out.
Nothing? Okay, so moving over to control, I'm going to keep it in theme with the senior design project, just because we're a little crunched for time in that course. We do have to pick up the pace a little bit. So for control, we actually are going to be building. For control, we need a few things. We have the actual STM board. This is our microcontroller. It was optimized for real-time control, so that's why we kind of chose it. It has enough inputs, outputs. And also, if you have any experience with Arduino, it has the same connectors that Arduino does, and you can run Arduino code on it. Very interesting board. But we will have our STM. We will have a safety team. And we will have a like more software, like code and testing control loops, stuff like that. So for this STM, we need to make sure of a couple things. While it is, like I said, 5 volt tolerant, we want to really limit the amount of times we're getting near 5 volts in there, and absolutely do not go over it. These things, they like to die, so they're cheap. Luckily, the boards are about $15. I'll send out another link again if you want to get one and start playing with it. But we need to make sure that all of our stuff is 0 to 3.3 volts. Power-wise, we will get it from the PDU right here. That's going to be supplying all of our power to this STM, so that it's easy enough to switch in and out. These boards are reconfigurable, so they take a wide range of voltages for power supply. You can use a USB cable, you can use 3.3 volt input, 5 volt input, and then 7 to 12 volts DC. So for the STM team, They're going to be working a lot with a PCB. So we are going to be designing a PCB this year because our board has male connectors on the back, so it just slots right in. But it uses the same kind of wires that you would use in your breadboard, and that's not secure. It's not; those can fall out during the race, vibrations. We don't want that. So we are going to be designing a PCB that this board can drop into. We're also going to have an extra one on board so that if anything happens to this, we have another one that's preloaded. You take that one off, put the new one in. It should fire right up and work exactly the same. That gives us level of redundancy. They're going to be handling all the sensors. We are going to have two types of connectors. So we need a wiring harness here. So one of them is going to be for Molex. We want to be able to quickly connect all of our bigger sensors that are discrete that we didn't design ourselves. This is the same type of connector that you'd see in a desktop computer. So if you've ever opened a computer, we're going to be using those. Now the other type that we're going to be using is it's a screw terminal. So essentially the reason we want to do this is because some of our inputs, we're actually just going to be using some simple voltage dividers. They're low enough power and they're simple enough that we're a little less concerned about, super high accuracy. Like we don't, as long as we're within, say, 10 of a volt, we're fine. So 2 decimal places coming out of our batteries and stuff. So these are just going to have direct wires, straight off the battery. For example, if we're monitoring the battery, it's going to have wires coming straight off of it. They're going to land in the screw terminal, and then the sensor is actually going to be part of the PCB. Is everybody following? The reason we're going to do that is because it cuts down on cost. Not having to buy extraneous sensors. I was looking at voltage sensors. We can implement them for a couple dollars, and if we bought them, they could be $15 to $25 a piece for things that are relatively accurate and at the ratings that we need. Next, we're going to go to safety. Our throttle actually is going to be 0 to 5 volts. We're going to step that down to 0 to 3.3 volts. That then goes into the STM. And then when it comes out, we're going to have our throttle signal still being, or we'll actually have 2 throttle signals. We'll have 2 throttle signals because, as I said, our motors are independent. So we need to be able to control them independently so that we get those real tight turning radiuses for the slaloms, which is kind of like an obstacle course, between relays. This is going to go into safety. We're going to have a relay for each of these. We're going to have a relay for each of them, and then that's going to the all-tracks controllers before it hits the motor. So because this is 0 to 5 volts, we get to do this really cool thing where if we switch these relays to our alternate signal, we actually just run the motors directly off the throttle. We skip the STM step, so if this STM board fails and we're having trouble getting it working, we can keep driving the motor. We will have, I believe the current plan is for the steering for the rudder to have mechanical backup, so that way in the event that this happens, we flip a single switch, and it just goes to like the standard control scheme. This is gonna be super simple, but it's really important that we get it right and we get the order of the switching down so that we don't, mix voltages where they shouldn't be mixed or send them down the. Yes.
I just don't know, but what's the benefits of running it through the STM if you can just run it through the mechanical instead?
So the benefit of running it through the STM is actually that we get independent control of the motor. So instead of having them run at the same speed, we can actually slow one down and speed the other one up using our control loop, which is what the software team can be responsible for. And that enables us to use differential thrust. So when you speed one motor down and speed the other one up, so let's say you slow the left one down and you speed the right one up, you're actually going to turn left. And for that, you actually don't even need to use a rudder. The rudder is just there to improve that turn rate. Because we did have a problem this summer when we went to Ohio, where when we were racing the slalom, our boat was quite long, and two had poor steering, and so to avoid making contact with the buoys, we actually had to swing really wide around each of them, and that cost us a lot of time. Like I think our slalom was 150 seconds or something like that, and the winning team was like 30. Yeah.
Because we're using just a rudder, not only were we having like going wide, but on our final turn, because the rudder is mechanical, it was actually straight on the radius. So you had to make a bigger arc just to not get moving.
Yeah.
We just had to our turn.
We could turn right faster than we could turn left. Yeah. Like it was quite a lot. It was like 30% faster, 40% faster, something like that. It was a really significant difference, and also our angle was quite dramatic. The tilt. So yeah, we want to be able to switch over just so that in the event anything happens, we have a backup for a backup for a backup. That's the big thing is we want this situation to be adapted, or this system to be adaptable to other needs, because I'm going to release it to all the other racing teams once we're done. Because I know they've had problems getting data acquisition, electrical controls, and all that stuff working in the past. And that's kind of my background. I've been a controls tech for 5 years. Yes, okay.
Bottom left. That says mode.
Molex. MOLEX.
Okay. Thank you.
These connectors are quite good because they're relatively cheap. I already have all the tools to make them, and they're secure. So we've used these in industry a lot, especially for motor control stuff that has vibrations and not many problems with them. So that's why we're doing this. For safety, we also have like stuff like a dead man switch that you guys are going to be responsible for. So if we look at the on-tracks manual, which I did send out in the announcements, I believe the other day, we actually need a dead man switch, meaning that we put a lanyard onto the skipper, the person who's driving the boat, and if they fall out, it disconnects that switch and cuts power to the motors. So we need a bunch of stuff like that. And then finally, we have a bilge pump. Does anyone know what a bilge pump is? What's a bilge pump?
I did a solo boat competition like in high school, and like from what I remember, a bilge pump pumps out water that's inside the boat as it goes in, and it has like a buoy type thing that floats. And
Correct.
Once enough water gets in, it'll start pumping out.
Yeah. So we actually had a problem with our bilge pump too. Big surprise. We had problems with everything.
Also, on that note, if you are working with a bilge pump, you're going to also be directly working with our solar mount too. Because we might cool our panels. If we are cooling our panels, the connection of the bilge pump may be running through our panels and out of the side.
Yeah, because solar panels in direct sun, they run at about 70 degrees Celsius, and you lose it's what, 0.5% or 1% per degree Celsius above 25 C. Yeah. So it's actually quite a big difference in terms of efficiency. We'll see if we have the money to do that. I think that's the better question, if we have the money. which is fine because if we don't have it, we'll just optimize better. Yeah. So where was I at? The safety. Build problem. So yeah, we had a problem with our build problem. Our float stuff. It was awful. So what we did was I rewired it so that we could just run it directly off the switch. So the skipper would have to turn it on manually every single time, which meant, well, not that we ever had to turn it off, but for a large portion of the race, the skipper was sitting in a relatively deep level water. So we don't want that to happen yet. So we have our build. And that's going to be part of the safety ticket as well. So anything to do with switching, anything to do with our like interfacing, like our HID, is that what it's called? Human interface devices, something like that. Anything to do with anything that the skipper is actually touching, that's going to be responsibility of the control team. Finally, go to software. Sorry guys, it's all control loops. Good luck. This is probably the hardest part of our entire project. It seems simple, and it is simple, but the amount of tuning it requires is huge. Which we can't start even tuning it until we get all of our sensor data that we need for control. We'll publish a sensor list. Actually, I can pull that up right now, so I can read you guys off like what kind of sensor we're using for what. Sensor list? Yeah, I do. I can send it to you. Yeah. So up here we have our sensor list. For things like control, we're going to be doing throttle. We need to check our steering angle, so we need to check our position of our rudder off from normal. We need to know like how much torque we're putting through our propellers, like how much torque is going in, because we need to make sure those are matching. Same with RPM. We need to make sure those are pretty close. Because if we don't, the boat's going to start turning, and that's kind of annoying if you don't do that. For our motor, they actually already have built-in temperature sensors, which is really, really cool. It makes it really, really easy for our sensor team to integrate those because they're just thermistors. So I believe they work with any supply voltage. They should. I think so. We have at least like 2 years, so we'll see. We'll see if they can work. If not, we'll get some thermal cement and mount some new thermocouples to the motors. But we need to know our RPM, like I said. We need to know our power draw. This is huge for maximizing efficiency. We need to know what we're taking out of those batteries. Because they can only supply so much power, and that decays over time. And we need to make sure that as that's decaying, we're slowing our motors down or speeding them up, whatever's more efficient, to maximize like the number of times we're getting our endurance. We also need to know like our voltage to make sure that it is stable. We want to know at all times what all the voltages are throughout our whole system, and then that's going to be displayed all on this digital dashboard. Anything that's really important is going to have the skipper's going to have immediate access so they can see in real time. I believe we're putting in electrical in the boat endurance. I believe is what I discussed with Liam, because that is where the electrical knowledge is going to be the most important.
So if y'all are in the book for 2 hours, y'all gotta get real knowledge.
Yeah, you have to know what everything's doing. I will be in the boat this year because I didn't get to do it last year. Which is probably for the better, anyways, because I was uncomfortable. Coming off our panels, we want to know our voltages, we want to know our currents, we want to know what's being generated, what are we putting into our charge controller. We want actually to intercept that stuff before it goes into the charge controller to make sure we're not damaging anything that we're getting good numbers out of it. And also so we can see a change in real time. For batteries, we are going to be doing voltage and current sensing. We're going to be using, I believe, DC current transducers, the magnetic type that climb onto the wires. For voltage, PCB job. We just want to put those wires straight onto that board and have the board handle the rest. Then we're also going to be doing a lot of calculations with that. So we're going to have to get real familiar with battery charge curves and stuff like that. Again, there's going to be a lot of crosswork. So don't think just because you're on one team you're not going to ever do anything else. We'll have a lot. It's a big system. Like I said, I want it to be modular. So got a lot of stuff to do. And then I think we're doing gyro and accelerometers because our mechanical team actually requested vibration sensing on the shaft, so on the shafts for the motors, so that if you get too much vibration, we throw our motors down, and that way we don't damage the boat or destroy bearings or anything. Anything that's really hard to fix at the competition.
Are we not doing temp anymore for battery?
Oh, yes, we will be doing temp. We want to know our battery temps. That way, if we get one that's at 85 degrees Celsius, like it was last year, I almost burned my hands through my gloves. We know that before it gets that hot. So once we see that battery temp start to spike, we know, hey, this battery's bad. It wants to off gas, and we need to pull it out of the system. I believe we had a defective battery from our battery sponsor. What happened, which it happens. Pressure builds up, it cracks, and then there's current flowing where it should be. I'm still not 100% decided on if we want to have a 7-segment display backup for our really, really important data, battery voltage. That's really important. If you have ideas on how to implement that for a relatively affordable price and also not a lot of code because we have too much code to write already, that'd be nice.
If you guys really want to suffer, you can also make it purely controls. You guys remember what was the course?
Microcontrollers.
Yeah. No, before that. The one track.
Oh, digital logic design.
Yeah, you have to use digital logic as well.
Yes.
You would suffer, but you could use digital logic.
It would be helpful if you are newer EC student.
There's some 7-segments that just take 2 wires and it outputs a voltage that's across those 2 wires, like on the 7-segment. It comes like that.
I have seen those. If we are going to implement it, I would like to build it just so we know exactly what the schematic is and all the PCB and whatever electronics we're using, exactly what that's doing. But we can look into those and maybe try to build something similar to that. I believe a lot of those are microcontroller based, though. I believe they're microcontroller based. Any questions? Yes.
So what is the 0 to 5 volt throttle?
So essentially, it's a 10K pot. So you have a 10K pot. You take a 5 volt signal in, which it might not be 5 volt in. We'll visit that in a second. So you have your input, 10K pot, then you have an output. This output, we care about it being at some point in the chain. This needs to become 0 to 5 volts. Now, if we do voltage divider coming out, we can actually just use, yes,
On throttle, I think you're using the dual throttle, right? Coming out.
yes,
If so, I believe one of them is 0 to 10K and the other one's
10K to 0.
It's
It's
the
the
opposite. It might even be. I think it goes. Behind the one.
Something like that. Anyways, our throttle is essentially a fancy 10K pot with a switch. So right here you have, you have your switch and then that can, open and close. So that way when you get down to really, really low throttles, it actually completely disconnects so that it shuts the motors off. So you get a true 0 volts coming out of the pot. We may do something closer to like 12 volts in, and then voltage divider after this, just so that when we build this PCB, we can guarantee that the signal that we're getting there with the complete resistance of the loop is dropping down to 0 to 3.3 volts, or somewhere near there. It doesn't have to be exactly 0 to 3.3, but I would like to keep it on the floor. And I believe the current ratings are somewhere in like 30 to 50 milliamp range for the microcontrollers. So we just have to make sure, but it might be in the hundreds, maybe like 150 on the ones that we use for the throttle. I know there's a few different like current ratings depending upon exactly which things you're using. I did send out that manual. I know it is long. If you could skim specific parts of it, if you're doing anything with control, that would be really, really helpful. I can't do it all myself. Any other questions?
So like, what is it specifically like mechanically measuring, and where's the input voltage coming from?
So the input voltage is either going to be from our KDU, or it's going to be from the STM, depending, once we do some testing, if we can guarantee that that's going to be 0.5 volts on the output. Just because with this relay system, we actually run into a little bit of an issue if we do the voltage divider, unless we completely replicate those exact resistances on the switch side or do it after the switching. Well, we can't because of the STM. But we actually run into a little bit of an issue if we use the voltage divider because it adds more resistance to our loop. So that's just, yeah. So that's why I was like debating taking this out, but I really would like to keep it. And it doesn't seem that much more complicated to actually implement this. It's a 3-position switch and a couple relays and maybe some resistors. And we can even take a small breadboard and then seal that completely once we make it. So make sure nothing comes out. But this is just a simple potentiometer. Well, it's a fancy potentiometer, but that's all it is. It's just a sweep in the track, a little bit of a lever that we can, pull the throttle and then it'll spring back, so it turns off. Did I answer your question?
Yeah. And then also, could you explain the relays again? Like, what are they meant for?
So these relays, our Ultrax actually takes, I think there's 13 different types of inputs that you can have. It's very cool. The ones we use over the summer is 0 to 10K setting, and that actually uses the full 36 volts on the battery system, which we don't want to put that into the STM. It'll not be good. So we actually are going to be switching to a 0 to 5 volt system. So what we're doing is we're essentially creating like, I don't know if you guys have ever like read into like racing sims, like flight sims and stuff like that. A lot of those throttles are actually 0 to 5 volts because they get their power from USB, and then they step stuff down and do whatever logical they do, put it back up, send it back out. But their main supply is 0 to 5 volt throttle. So we're essentially making what you can buy off the shelf with just a simple 10K pot. The reason we want to do that is because, like I said, our motor controller can read 0 to 5 volt inputs. then these relays are going to switch it over. So we're going to bypass the STM completely with these relays and just go throttle into both all tracks. So if we switch it, we actually will get something like this. We actually will get like throttle. That's going to go idle throttle, and then that's going to go into both all tracks motor controllers. And then that will go to your individual motors. So what this is going to do is these motors are actually going to run at the same RPM, regardless of if we're turning or not. Just in case something happens and we can't get our STM back up and running, we can still keep the boat moving. That's really helpful, especially even if we lose our steering, like say mechanical backup fails, electric fails, completely without steering, it still helps us when they're towing us in. Or you can change direction with your, you have to have a paddle on board. You change direction with the paddle, and you can still, power in a straight line just to make it back to the shore without having to call for a tow. So super helpful. Makes things a little bit safer for everybody. Generally a good thing to have bypasses on your control stuff if you need to do things manually. Any other questions? Answer? So let's take a little bit of a break. I know I've been talking at you for about an hour straight now, so go ahead, get some refreshments, use the restroom, whatever you guys need to do. We'll come back in like 15 minutes, 10 minutes.
My hardware problem. And it's really hard to say, to tell your hardware dude to like, hey, can you rebuild it again? After you do like the second or third time.
Later on, you're gonna do stuff.
It didn't work this time.
Anyway, we're starting. So I wanted to gloss over a couple of things that I forgot to tell you guys. For the PCB design software, I was sent a document last night debating the pros and cons of the 2 free softwares that we were looking at, and it looks like we are going to be going with Altium. I believe that's how it's spelled. We're going to. Huh? These are used. So we're going to be going with Altium. We have looked into using KiCad, but it looks like the libraries are not fully managed by the software. So we don't want to deal with, especially newer people, needing to install like a billion libraries to get all the functional parts that we need. So we are going to be going with Altium. We may explore KiCad. We may explore KiCad, but just kind of plan for using Altium if you want to do anything with PCB design. That's the most robust one, and I believe, is everybody here electrical and computer engineering, or anyone we have is different? No? Okay. I believe we do, as engineering students, we do get that software for free through the school. So we're going to try and use this. Second, we're going to try and use LT Spice. We're going to try and use LT Spice for our sins and stuff because it is completely free and there's no like worries about like trying to make accounts and redoing trials and stuff like that, like PSpice and stuff has. So we're going to try and use this. If anybody runs into any like problems, because I know there's certain things that you can't simulate with LT Spice that you can with PSpice and stuff, come talk to me, come talk to Eli, come talk to like whoever's leading your thing and have them reach out to us. We need to know kind of what's going on with that. With that being said, any questions, comments, concerns? Alright, we're gonna move into control. So could you pull up that sensor? We're gonna move into sensors. So this is a sub-team on the senior design project that is not part of the club. The reason we did this is because it makes it easier for our senior design project advisor to grade us, and it keeps us a little more streamlined. So I believe we have one group of 5 and 3 groups of 4. A lot of people, it just breaks down easier that way. But like I said, we did pull one person from power, and we did pull one person from control, and the other 2 are from the original data acquisition team. So I think I should break it down by how it is up there. If anybody has anything against that, let me know. But let's start with the motors. What do we need to sense, and what are their voltage ranges? So for the motor, we need a few things. We need our motor RPM. We need our power draw. We need our motor temperature. And we need our motor torque. I'm going to put a little star there because I need to talk to mechanical and make sure they still need that, because we are actually doing vibration sensors now, so we may not need to actually check our motor torque. We may just be able to look at the vibration sensor and the RPM and kind of approximate, hey, this is good to go, like we're running at, or with the power draw too. As the load changes, we'll be able to see if we're getting relatively accurate performance. And then the final thing we need is the vibration sensors. So how are we going to do all of these, and what are their voltage ranges? I have had a couple people look into Hall effect sensors. They're super robust. They do not care about water. They are really accurate, and basically everything that we need is super good. So we're going to be using Hall effect sensors. Does anyone not know what a Hall effect sensor is? So Hall effect sensors are really cool. When you pass a magnet in front of something, obviously you're generating a current. Well, what this Hall effect sensor does is it takes a moving magnet and converts that into a readable signal. So what we're going to do is we're going to have our motor, and it'll have a shaft coming off of it. We're going to put a magnet on there, and we're going to have the Hall effect sensor read this magnet, and we'll be able to see that rotation. So as this is spinning, the faster this is detecting a signal, like it'll detect like a flip of current every time the magnet passes in front, the faster we know our motor is spinning. Again, all of these will have some type of mathematics and calculations involved, but they should be, I think, all algebraic, very simple, just like stuff you would see in intro to microcontrollers, if any of you guys have taken that or are currently in that. This is the kind of stuff you start to see towards the end. For power draw, this is actually going to be 2 things. So we have a voltage sensor, These ones we're gonna buy. Just because the voltages are quite high and we want to test the full 36 volts, we're going to buy these. For the other voltage sensing, especially the batteries, we can actually break them down into their separate battery voltages in our pack. So they're only up to 12 volts. We can do that with super easy with resistor. But I want to interfere with the motor as little as possible. For current sensing, we have DC current transducers. Now, we have to get very specific when we buy these. These motors are 8 kilowatts each. That is volts times amps. At 36 volts, that means we are going to be pulling, I think it's 445 amps per motor peak. So we need to get current transducers that are rated for 500 amps. For 450 combined, sorry. Roughly 450 amps combined. But I want to have on matching DC current transducers, because also for this, we are going to be using the same one for a battery. And we want to make sure that when we are getting sensors, that we are using all of the same sensors. For documentation purposes, for testing, it makes the translation between those numbers a lot easier because they'll have the same sort of defects, they'll have the same sort of tolerances, and it just makes it easier for us to see and easier for us to buy. Buying multiple of one thing is often easier for us than buying a bunch of separate pieces. So for these have to be purchased. Next, we're going to move to temp. So there's actually an existing thermocouple. Does everybody know what a thermistor is? Raise your hand if you don't. So a thermistor is a calibrated resistor. What it does is it changes its resistance value based on the temperature. I believe from the manufacturer there is probably a specification for exactly what that is. It is probably NEMA Class 2, which means it is accurate from about freezing to maybe like 150 degrees Fahrenheit. So we shouldn't ever really be more than that. If there is, there's a problem. So we have to test these, make sure that these existing thermocouples are in fact still functioning, test their resistance values, figure out exactly what type of thermistor they are. And if not, we can buy new ones, and there are compounds that essentially create a thermocouple using the thermistor. So a thermocouple is an applied thermistor. We can manufacture these relatively easy. They are affordable and really easy to program. So and read those values, because like I said, just a resistor. Torque. Not sure how we're going to do this, if we're going to do this at all. So if anyone has any ideas or wants to look into this, please let me know, and I will put you in touch with our mechanical lead also, because I don't know if he still wants this as a requirement. I know he was talking about it originally, but with the other sensors we added, it is less of a big deal. Vibration sensors. This is actually going to be using a leftover, this is with an accelerometer / gyroscope. These are like packages that you can buy. It's just a little chip and has a couple inputs and outputs, similar to what you guys would see like in your like digital audio class, like the LS, like whatever LS chip. we do have to read these. I don't know exactly which ones our mechanical lead wants because I know he found ones that are easy for him to mount. That was a big thing is to get them on there stable, and we're responsible for everything behind the mounting. So after those sensors are mounted, we're responsible for the wires, for programming, the reading. They're responsible for getting that sensor put where we need it. Or where they need it in this case because they have to really integrate it with the rest of the design of the boat mechanically. Any questions, comments, concerns? Any sensors you think I missed?
Well, for the vibration one, will it like sense the overall acceleration of the boat as well?
So we actually are getting these in a 3-pack, and we will have a third sensor available to do that with. These are going to be purely for sensing the vibration of the shaft. Because the boat's made out of carbon fiber and it is a composite material, what happens is if you get too much vibration, carbon fiber doesn't bend. It shatters. It breaks. That's not good. So if the vibration gets too much, we throttle the motor down until the vibration stops and then we speed back up again. Shouldn't be much of a problem. In fact, if it is a severe problem, there is another issue with the boat that we will have to address on the mechanical side. But we do want to know, like, hey, when we do this kind of throttle input, it starts to vibrate. So we need to delay it slightly or slow that curve down a little bit and make it a little more progressive so that we don't get excessive vibrations out of our motor. I believe the way that's going to work is that's just going to be mounted like right on the back of the motor, like there'll be a chip here. I believe that's how he has it. He might be mounting it to some connection to the shaft or something. I don't know exactly what he wants to do. He hasn't fully figured it out. Yes, question?
All movies take into account for the maximum right?
No. So for the Hall effect sensor, it shouldn't be a problem because the poles are not fully aligned, and it's counting for that rotation. So any constant like flipping is probably not going to be an issue. We will be looking into that more, and we do have an alternative sensor that we can go with, and that is a laser tachometer. So if we don't do this, we will be going with a laser tach. And that is just, you make sure there's a spot that is a different color on the shaft, and you point the laser at it, and every time it changes color, it counts because it can read that difference in the refractive properties of the color change. For these, they actually don't need to be near the motor itself. They just need to be coming out of the wherever the wire split off. They can be near the all tracks. Don't have to worry about the magnetic field. These are really cool because we actually don't have to worry about the magnetic fields because those gyros are spinning super, super quick. Yeah, they're really accurate. So all of this should be far enough down the shaft that the motors spinning themselves are not much of a problem. Because I think we have a foot or two coming out of the motor to where we will have to be able to mount stuff. We will be working with mechanical more on that. That's more of a main thing to make sure we have the correct access and stuff. Any questions on the motor sensors? Yes.
Like the specific sensors we have like already picked out, or that's something we're gonna decide later.
We have been doing research on that. I will publish that as part of a full document. What we have looked at, I haven't been able to read the information I was sent just because I got that last night pretty late. So I do have a couple ones we're looking at. I think that's it for motor. Should be next. panels and battery or control? Alright. So next, I'm gonna lump these in as one. We have panels and battery. So the current setup for our batteries from last semester or last year, which we might change, we actually have we have 6 batteries. So each one of these is 12 volts. We're going to sense them independently. Our biggest reason for that is one, once we get those sensors in to the board, the math is easy. It's just additive. 2, we had that battery explode last year. Does anyone know why that happens? When you charge AGMs too high, they can reach as high as 18 volts, 16 volts, somewhere like that. Their maximum is supposed to be around like 14 and a half. When you overcharge them, you get unnecessary heat. That causes the the sulfuric acid to turn into a gas. You overpressure your battery, you crack it. When that happens, it lets the battery off gas, so the charge kind of slows down a little bit. But you get an internal current that is low resistance. It's really bad. That's why the battery got super, super hot. We don't want that to happen. So we want to keep track of our batteries and make sure they're not going above, say, 15 volts. Now, the way we're going to do this, voltage divider. The reason I'm okay with going with a voltage divider is because we know what our peak voltage is. We know it's never going to go past, even on a way overcharged battery, we know it'll never go past 18 volts. The battery is gonna pop and crack before it hits this point. So we can separate it into 15 volt range on one resistor, and then this last resistor is gonna have proportionally a 3 volt drop. We read this resistor, we know each of our battery voltages, and that makes it really easy to read each one. And it also gives us the option to where if we need to say we're running out of inputs, we can take this off and do it on a whole other board and not really have to worry about it, because we will be developing those sensors with this Raspberry Pi. I believe that's where the battery sensors are going to go. Yeah, because I don't think they're important for control. So this is, we're going to have a voltage sensor. This is going to be a voltage divider, just because they're cheap and relatively low power. Obviously, we could go lower, but at the current we're talking about, it's not enough to be worried about it. Now, for the current sensing, each one of these packs, or each one of these, I guess it'd be a cell, you actually have 2 banks, 36 volts. So, because each is 12, then you'll get 36 volts here. We are not allowed to go past this in our rated battery voltage. So we will have 36 volts. We can read that independently. We can also read the currents coming out of each bank independently. How are we going to do that? Current transducers, our favorite. I don't care necessarily if we read pack draw or bank draw. So either one sensor or 2 sensors. On this side, there will be 1 sensor or 2 sensors. We can read both. Eli, is that something you would want? Independent bank voltages if we go with this 3x2 setup again?
No, we only need one.
Okay.
As long as you know something goes on.
Yeah, that's what I figured. So we will have one current transducer on the output of the battery pack, and that's so we can compare total pack draw to motor draw. We want to be able to see that because then we will know how much power we are dissipating before we hit our motors. So we'll have one transducer on the output. From there, we will do calculations. Oh, let's take a step back. We have one more sensor for each of the batteries. There's a temp sensor. I guess you guys could probably figure out why I want this here. Even if our voltages are high or low, you can still have problems with the battery. Our battery was 12 volts, 12.3 volts or something like that, and it was still off-gassing, and it was super, super hot. So we want to know temps, and the way we're going to accomplish that is a thermistor, and we are going to use thermal cement. So it's basically epoxy that has a really high thermal conductivity, and it will bond it to the plastic body of the battery. We may have these in different points, and we also maintain the air temperature, but these are so easy that I'm not really worried about them today, because I've done this for a living, and it is not that difficult. Just a resistor. For calcs, we actually want to know our charge percentage. This is really, really, really important for the endurance, and not much else. It is very useful to know because we are allowed to come to competition with fully charged batteries. Once we get to competition, we are not allowed to charge them except off of our solar panels. So the solar panels do not really do much for us during the races, but they do power our vehicle. So once we get there, it's all solar, no more wall power. So we need to know our charge percentage to make sure our batteries are charging sufficiently and that we are getting the right amount of power out of them, because we may need to. Are we still possibly building a solar panel? Probably not. Okay. Because the panels we are going with, we actually are not meeting our maximum of the wattage we are allowed to bring. If you buy panels, you have a 720 watt maximum at Solar Splash. If you build panels, you actually get up to 796 watts, but that's because they take the cell power rating and not the entire panel power rating, and obviously you get power losses from like diode feedback protection and stuff like that. But since we are not going with the full amount, we really need to be aware of how our batteries are charging and maximize, that output. We are also going to be calculating our power out. So this is the responsibility of the panels and the battery team. Well, I guess this is mostly batteries. Now we can move on to panels. Same thing. We want our panel bank voltages. So obviously we have 4 panels. We're doing 4. Yeah, we're 4. So we are going with 4 panels, which means we are going in a 2x2 configuration. Panels are rated for 20 volts, about. So we will put 2 banks of 2 in parallel to maximize our current and our voltage, so we are not changing voltages significantly over our entire system. What are we going to need on here? Voltage sensors. We can build those. Super easy. Same as this. I want to take each battery. And each panel. I want to know what the voltage is here, what the voltage is here, what the voltage is here, what the voltage is here. The reason I want to know that is what happens if we scratch our panel, our voltages are mismatched, they get covered in water, we see voltage drop due to cloud cover. We want to know if one of our panels is exhibiting signs of failure, of defects, so that we can orient them in this bank layout in the correct way to maximize the amount of power we're getting out of them. So that is something we will need to test. It may not be as useful during the race, but for next year's team, we want them to have as much data as possible. That way they can make the most efficient boat that they can get. Same thing with the current transducers. We will have one. That will be on the input side of the batteries. After the charge controller. We want to see just what the current coming into the batteries is and the current going out. It helps us calculate power generation. So because we'll know the voltages across these, we can calculate how much power we are currently making at any given time. Our motors cannot run off solar. So drip charging those batteries as much as we can is really, really important, especially for the endurance race. So we will calculate charge percentage, we'll calculate the power out, and we will calculate the power in. Now we could probably do this, honestly, without using the current transducer on here. Probably do it on the motor, but we get a little bit more accurate data if we do it this way. Any questions, comments, concerns? Stuff that you think I missed, stuff you think that we should be sensing that I'm not thinking about. Yes.
The charge percentage, we're just calculating that based on overall voltage and what we're measuring at? Correctly?
Yes. So all AGM batteries have a charge curve. Our solar charge controller actually does that power point tracking for us. We don't necessarily need to do that, but to calculate our charge percentage, we will need to figure out our batteries. Another reason we need to cycle them, we need to be taking data. What does their voltage look like at full charge? Like, when does it stop going up? What does our voltage look like when the battery's completely depleted and doesn't do anything? That curve is not linear. So we have to take a lot of data to figure it out and to run this calculation. Again, this is just so that you can look, like, you don't want to look at your phone and see, oh, my battery's at, 4.8 volts. What does that mean to you guys? Nothing. That's why we want this number to be a nice big graph that looks like a fuel gauge, so that we can see in real time, what we're doing. Or even also, once we calculate this, we can calculate how much charge are we draining per minute. Very, very nice for endurance races. That is what a lot of this system is for the endurance races, for maximizing that efficiency. The sprints and the slaloms are so short in comparison that if anything goes wrong, your time is trash. Like, it essentially doesn't matter. Because they only take the best times. Except for the endurance, where they count your total number of laps for the entire race. For every endurance race, your total number of laps is super, super important. For the other two, it's just your best time. Any questions? Yes.
So we're mainly worried about the endurance race than the other two?
This is where sensing is the most important in terms of control and power and data and the software data acquisition stuff. We are concerned for all of them because we want to see like what the boat's doing. But in terms of sensing, like the most important thing that we're doing here is trying to maximize our endurance race, because not only is it counted over the total of all the races that we do, it's also the most important factor in our score. I think the endurance race counts for 25 or 30% of the total like overall score, which is a lot. The other two races, for example, we got 5th place in the sprint and 5th place in the slalom. We got 6th place in the endurance. We lost by a lot. It wasn't close. It wasn't even close. Even though our tech report, our video, all that, those scores are relatively close, and we didn't get last in the sprint and the slalom, we still lost by about half of what the next team above us had. So the endurance is very, very, very important. And that's why we are doing everything we can to maximize our efficiency. So probably 36 volts, keeping those voltages really stable, doing a lot of sensing, monitoring our power because Ohio does get cloudy, especially in the summer. It was raining randomly for 10 minutes at a time. The most extreme downpours you should ever think of, and then the sky was clear again. So very interesting weather there. We do want to. That's why we got to keep track of what we're doing because we don't know what it's going to look like until the day of the race because it can change in like an hour. Any other questions? Any comments? Anything you want to add? All right, so that brings us to our final stage of sensors. Control sensing. This is where things need to be precise. We need precision, we need accuracy. Can anybody tell me what happens when you do not have precise sensing under control? Can anybody tell me? Come on, Sam, you got it. Let's say you are trying to turn the rudder to 5 degrees, and your sensor reads 6 degrees. It's going to turn not nearly as far as you need it. Or sometimes it'll say 0, and it'll keep trying to turn. And it is turning. It keeps turning. And it breaks. Because your sensor's not reading anything back. So I have seen bad sensors kill $15,000 motors in less than an hour. I have seen a bad sensor. I used to build clean rooms. I've seen a bad sensor destroy an 8-month long project. It cost the company $125 million for a $500 sensor that went bad, that they missed on the changeout time. $125 million gone. Then it starts from scratch. They lost all their testing. That is why control is very important. Your sensors need to be precise. They need to be accurate. Now, what level of accuracy are we talking? For the rudder, we want it to be within 0.01 degrees. Especially because it is a mechanical system with an electric assist for precision, we need our sensor to be really accurate. That's why we're using a stepper motor as well. So for the sensors, we also have a stepper motor. And do you guys know how a stepper motor works? Raise your hand. Stepper motors are really cool. They are like similar to like a ratchet, right? When you turn, it locks it in position. Well, because you have definite positions, you know exactly how far your motor's turned. So I believe the one we're going with has 4096 steps or 1024, but in each direction. I think it's plus or minus something like that, because it's science. So it's something like this: 4096 total steps, or plus or minus 1023. So we will know our definite position from the stepper motor. But should anything happen, we get water in it and it causes the shaft to seize or something like that. We want to know, hey, is our rudder moving? If it's not moving, we have a problem, a big problem, because that is our main method of steering. Because remember, we can turn off our differential thrust. We're going to be able to turn that off. So our main method of steering is our rudder. That is our primary form. If we lose that, we tow the boat. It can do way more damage to the hull and stuff. If say your turn, if you're throttling into it, it can put a lot of torque, and because it's going to be made of carbon fiber, it doesn't bend. Carbon fiber does not like to bend. So what do we need for our control sensing? Throttle, obviously. This is our one that doesn't necessarily need to be accurate, super accurate, because we can make the accuracy ourselves. Because we will be doing sensing from it with resistivity. And it's just a 0 to 10K plot. Turn into a 5 volt, 0 to 5 volt throttle. Because we know it's a 0 to 10K plot, I think it actually only hits like 8.6K, but it's alright. Well, we'll do some testing and figure out like what the full value is. This we're not super worried about. It doesn't have to be super accurate. All the other stuff is going to tell us what's happening with our motors, and if we need to turn anything off. We'll know from there. Throttle, we don't care. So next, we are going to have steering angle. Does anyone know the sensor type that you would put on the steering wheel? It has a specific name. It's called a rotary encoder. It's essentially a very calibrated fancy potentiometer. You can also use Hall effect, but I think we're doing a standard rotary encoder just because it's a little bit easier for us to deal with, and the level of accuracy is not significantly different, and they're also cheap. So we will be using a rotary encoder. With this, in conjunction with our throttle, we will be able to know exactly what our rudder is doing, exactly what our motors are spinning at. We can turn a boat now. Very, very good for us. Last year, the first time we put the boat on the water, our mechanical lead was the one driving. He designed the steering system. He's about ready to go. It snapped immediately before we even hit go on our first race. It snapped. Luckily, there was a team there that had a carbon fiber nylon 3D printer that let us print out the parts in carbon fiber nylon instead of, I think we had CPP before, which was not strong enough because our motors are 16 kilowatts. And we also had to cut the parts apart to make them fit on our square tree temperatures. That was why because we modified them from the original. But we're trying to get away from that, so that doesn't happen again. So this will tell us something super, super cool. Now, for the sensing on the rudder, if we don't know what our rudder position is, we can't tell if the system is working as intended. So we will be using another Hall effect sensor. Keep in mind, all these are 0 to 3.3 volts. Or they're 0 to 5 volts, and we have to do some magic to make them work with our system. But 0 to 3.3 volts for everything. Any questions? The reason we're going with Hall effect for the rudder is it actually decouples the system. Same reason we want to use it for the motor RPM. Nothing's actually touching, which makes everybody's lives easier. These are going to be split up actually between the Raspberry Pi, which is our data acquisition system, and the STM32. some sensors are really important for control, and other sensors are really important for long-term efficiency. So we don't want to overload our STM microcontroller with unnecessary data. So that's why we're putting the rest of it on the Raspberry Pi. The reason we don't want to mix stuff like that, if we can help it, is latency. Human interface devices, when they have latency, are really, really annoying. You ever been in a car with a touch screen and you try to touch it and then it's not loading anything, and then all of a sudden, all 15 of the times you pressed it all register at once? That's would not be good for something you're driving down the road, right? If your steering did that, you would crash your car, So we don't want to mix stuff. We want to minimize that latency. So anything I box in red is going to be the STM32. And anything I box in blue is going to be the Raspberry Pi. This is a Model 4B. We're going to be using a Model 4B because it doesn't require active cooling. I worry about heat, so we are using a 4B with 8 gigabyte, and then this is a G474-RE. Any questions on why we chose those?
Yeah, I was literally about to ask why we chose those specifically. What's the difference between choosing the STM32 and the Raspberry Pi?
So the STM32 is designed for continuous control. So the processor in it is a G4. I believe it's manufactured by ARM. Maybe I think it uses ARM Cortex, G4 cores. But that is optimized for continuous real-time applications. So the reason we picked that is obviously our drivetrain is real-time, it's continuous, it needs low latency, and that's what this guy shines at. The Raspberry Pi has a lot of overhead. While you can make it work for control systems, and I have seen it a lot in control systems, a lot of factories use it. It tends to not be for those real high-speed applications. What the Raspberry Pi is really good at is it has a lot of data capability. There's a lot of I/O. It has big RAM capacity. You can use large storage formats with it. Importantly, this can run Linux. This cannot. This has its own IDE development environment. Whereas this, we can use regular computer applications. We can use, if we get some Windows libraries, we can even use Windows stuff with it through emulation. So the reason we chose this is because we can handle our data super, super well. We need connectivity to a remote server. We need a lot of things that this guy does real well. And then this, super low latency, good for control. So the RPM we want on the STM. That way, if anything goes wrong, we can match it. And also we can introduce this into our control loops so that we are making sure that the RPM matches on both of our motors. Power draw, Raspberry Pi. Doesn't have an impact on our control, but we want to be able to see it still. And we want to be able to display on the dash, which I will get into in our next section. Temp for the motors, Raspberry Pi. Our motor temp is more about calculating stuff for efficiency in the long term than it is about the current temperature of the motors in real time. If we do see a problem with it, we will know because it will be displayed on the screen and we will make it have warnings. But otherwise, it's fine. Torque, if we do it, STM, we want to be able to modulate our motors based on the torque that they're providing if we do sense it. So it helps to have it on the control board because we are not allowed to write from the Raspberry Pi backwards to the STM. The Raspberry Pi can only read what the STM is doing. Vibration, same thing, STM. If this starts vibrating too much, we want to turn off our motors or slow them down to make it stop. Real bad thing to have happen, so we want to be able to introduce that to our control loops. Accelerometer and gyro. If we do this for the boat, it's going to be on the Raspberry Pi. We don't care how fast we're accelerating and what our speed is in terms of control. Doesn't matter to us. In the sprint, we full throttle it. In the slalom, we are more concerned about steering. And in the endurance, well, who cares? We don't want to be accelerating. That's bad. So we want to keep that out of our control. For the panels and the battery, anyone take a guess? They all go in one category, Raspberry Pi. This whole section is all in the Raspberry Pi. It's not necessary for control. Keep it off the STM. So we don't want to see unless it's on the dashboard, and we'll make our appropriate changes to our power curves and stuff like that if we need. Now for control. All STM. It's all in the STM. It's all really important to know exactly what everything in the system is doing. If we didn't have this, again, like I said, it'd be expensive. You want to get your control right to make sure the boat's working fine and keep everything moving smooth. Any questions? Yes.
Is the stepper motor to actually control the rudder, or are we using a hallback to measure it? Or what the stepper motor, what are we using that for?
The stepper motor moves the position of the rudder.
Okay, so it controls the rudder, and then we're going to use that also use a Hall effect sensor to measure where the rudder is.
Yes, so we can measure the position of the rudder using the stepper motor, but also Hall effect is more precise, and it tells us, more importantly, exactly what angle we're at, rather than the number of steps. So if our shaft gets slightly turned inside of the whatever the cradle that they're using, however they're attaching it to the rest of the steering system. If that shaft gets slightly turned, or that motor gets slightly turned, well, you just lost all the math that you did to convert those steps into the proper angle of the rudder. We don't want that to happen. So that's why we remove the hard code and we put a sensor on it, so then we can read that. Yes.
So on the rudder, are we throwing on the was it the Hall effect reader, or are we throwing on the magnet?
The magnet. The magnet goes on the rudder because that's the thing that moves.
Okay.
Anything that moves, you put the magnet on, because obviously you don't want your wires that are connecting to the chip to get spun up. That's another thing. You get fatigue. You get fatigue if you have solder joints and they weren't properly done. Say you have a cold solder, they'll crack, they'll fall off. Big problem when you're trying to put your boat in the right position. Anything else? Ask you now while I'm here. No? You like anything to add?
Oh, actually, I was wondering, Raspberry Pi is going to go as birthday using with our dashboard, right?
Yes. And we will get into that after sensors.
And then all of the STM, maybe, is the STM information going to the Raspberry Pi to red, or is it going to
Yes. So this is something that the software data acquisition team is going to be more responsible for, but our wonderful team back here discovered that UART was the best communication because it's purely supervisory, meaning that the Raspberry Pi cannot write backwards into the STM, which is something we want to avoid as much as possible. We want our systems segmented, we want them separate, we want them to be able to run without necessarily needing all systems online. That improves reliability, that improves the robustness of the system. It gives us a lot of benefits, especially in terms of like introducing error into the control loops. The more stuff you have interacting with your control, the more likely you are for things to go wrong. So we want to limit that interaction. So it just, all it does is it reads the data coming into the STM. The STM doesn't even know it's there. It's just purely supervisory. Any questions? All right, let's take a 5 or 10 minute break. I'm going to take pictures of the board really quick, and then when we come back, we're going to talk about data acquisition and the software side. We're going to get started on the software and the data acquisition side of stuff. So I know, programming. Nobody likes it. That's why we're electrical and computer engineers. Who wants to program? You do. Yeah, unless you do. Yeah. I just make programmer here. Actually, do that. Actually, don't. I'm done with those sensors and stuff. Okay, so I know we've been avoiding the elephant in the room. We gotta have code for stuff. The sensors, the Raspberry Pi, everything. What languages are we using? C. For the STM32, in particular, we are going to be using C. That seems to be the language that most people know at this school. And also, it is fairly fast and fairly robust and low latency. For the Raspberry Pi, because we're handling a lot of data, C++ for our data structures. We have to be dealing with a lot. We may also use bits of Python, HTML, smaller languages like this, but the bulk of our code, C++. It is the most applicable language for what we were trying to do with the Raspberry Pi. And it also helps that C, C++, and Python are built into the Raspberry Pi libraries. So, super nice, already integrated, got a lot of stuff to do. All those sensors that we had last time, we gotta log the data. Unfortunately, we have to keep track of a lot of data. So how are we going to be doing that? I believe the initial plan is for CSVs or arrays. We haven't fully decided how we're going to do it because we haven't started implementing. Now, we are going to be doing something called data twinning. So the Raspberry Pi we have a Raspberry Pi that is going to speak to a router over Ethernet. That router is going to be connected to an LTE hotspot. It's going to talk back and forth. The reason we want this router, we can actually, the one that we are going to use, I'll post documentation for it, is a little travel router. 2 reasons we want it. We want Wi-Fi for streaming. We want to be able to live stream to our social media pages from the boat in real time. Super cool stuff. Another reason is we can also store data on this. We can use this as a file storage server. So, the reason we want to do this, let's say our connectivity fails. we still want to be keeping logs of the data. We also are going to be keeping those files on the Raspberry Pi as well. We want to do both. Data redundancy is key. Data redundancy is huge. If you lose data, you lose a lot of money. There was a time where I was building a file server for a very large company, like Fortune 50. They did not keep a data backup. They were running RAID 0 on their hard drives. Does anyone know what that means? It means the data is striped across both drives. So if you lose one, you lose it all. They lost it all. Luckily, someone had a backup on their personal laptop at home. That backup was 6 months out of date. Every day that I worked on that system cost that company $15,000 for 6 months. And they lost it because they did not have the proper protocols to back up their data. Now, for us, it's not that serious, but we do want to keep redundant copies of the data. If we lose the Raspberry Pi, we still want to be able to pull everything off and be able to look at it. We'll be backing this up in our Google Drive as well after we take the butt out for a day. But we want to be able to keep separate logs for different runs and stuff. So we'll probably have a switch or a button that starts and stops data logging. So we want good data practices. After this LT connection, we'll have a server. The server will do two things. We will have graphical data and file storage and downloads. And remember how we talked about a digital dashboard earlier? This is going to replicate that entire digital dash. We're going to be able to see what the skipper sees in real time. Not exactly real time. Latency's fine.
I didn't interrupt you. How much longer do you think?
Maybe half an hour for this, and then if we want to split people into groups, maybe another hour after that. I can speed up.
No. I think for groups we're gonna have to meet online.
That's fine. Yeah. I do want to get everybody's. We'll make a Google forum, and I'll put it. We'll put it out, and you'll put your information in there. What sub team you want to be on. Obviously, senior design project people, don't worry about it. Everybody else, we'll send out a Google form on the.
Actually, do you have other stuff for your phone? I was hoping you guys will be here. You want to be here for your challenge?
I can keep talking. Keep talking.
Alright, so this week, probably this week only, we'll have Discord meetings throughout the week with your team. Make sure to actually join that. You'll get your tasks there. You'll talk with them there more. If Sean knows that and wants to do something else, that's okay. He's the electrical lead. That's fine. But for the most part, that's okay. So make sure to talk to your lead. So for my power people, you'll talk to me. I'll set something out. If your controls, Kyla doesn't know this yet, so let Kyla know. And then everyone else, Ajahn is here, Sean's here, so y'all should be good. But yeah, throughout the week, have a meeting at some point.
Yeah, I'm free. Don't talk to me on Mondays and Wednesdays. I'm not free on Mondays and Wednesdays. Anything else for game?
Be done by 2.
I'll be done by 2. So I guess we will not be meeting in groups today because I will talk the next 30, 40 minutes. Because this is only scraping the surface of everything. We already have some designs and stuff for voltage conversions, some basic hub blocks, some research on different sensors and stuff. But this is just the general architecture of the boat. And I'll be breaking it down into the smaller blocks like how we had it there. Maybe I'll have Angel do it because he seems to be intent. Yes.
Are you gonna be uploading the meeting? You're recording it, right?
Yeah, I am recording it. I'll upload it to my YouTube channel, and then I will drop the link in the chat. It's very long. Sorry, not really, but it's not my talking. So this server is going to host graphs of all of our data, as well as the files, and it's going to have a replication of our visual dashboard. The reason we want to see that is because someone who's not experienced or well versed in certain components of the boat may be driving the boat, and if they tell us, hey, the battery voltage, da da da, we tell them, hey, no, tell me which file or which data point name is listed on the whatever GUI we have or which gauge it is, and we'll do whatever counts or whatever you need. Like tell us exactly where it is on the GUI, and tell us what your problem is. Makes it easier to put newer people in the boat. That's something we want to be able to do so that people get practice. For the Raspberry Pi, we also are going to have a display. So the Raspberry Pi has a 15-pin internal connector. That means that it's a routing cable. The reason we want to do that is because it locks into place. Cables that lock into place, really good for things that vibrate, really good for things that move. We don't have to worry about stuff on that. So it's a 15-pin internal. I believe the current spec we're looking at is 1920 by 1200 p. It's a 12-inch 16 by 9 display. And it is, I believe, 1200 nits peak brightness. The reason we want it to be so bright, and the reason that that's going to be expensive, is because it is going to be in the sun. If it is in the sun and it's not bright, you cannot see it. So, gotta pay a little more for this peak brightness and also the higher resolution, even though we don't need it. Is typical of these higher brightness displays. This is going to display that GUI I was talking about, and that's going to have a whole lot of stuff on it. We want the battery voltages. We want the battery charge. We want motor, RPM. We want a whole list of other stuff that we talked about today. I'm not going to keep going into detail on it because we've been here a long time. All of these files are going to be packaged in a way that they are easily downloadable, parsable, and transformable into graphs. We aren't decided if we're going to do a master like CSV, which is essentially an Excel spreadsheet for those who don't know. Not sure yet if we're going to use CSV or we're going to store in arrays and print them out in real time. I'm guessing CSV is going to be easier on the graphical side and the data analysis side, but harder on the code. But I think overall, CSV for the most amount of people makes the most amount of sense. Any questions? All right. The Raspberry Pi, if it does fail, it will not have a backup. If it fails in the boat during a race, we do not have data logging for that race. They're a little bit too difficult to swap. It's not like PSTM where we can load a program on it and keep it as a cold spare and just plop it back down on the PCB, whatever we design. we have to actually take some things apart and make sure everything is up and running the way it needs to be. Though we can streamline that, I do know there are processes to handle this stuff through that startup. But the Raspberry Pi is a little bit more complicated, and we have to ensure like that it has the proper like IP addresses and stuff. For this file server, I was recommended stuff like AWS. However, I will probably self-host it. We do not have the money to afford that amount of file storage and uptime. If anyone has any questions on that, ask them now. Yes.
What is the cost? Like how much?
The problem is that it costs money in the first place.
Yeah.
I believe for like our needs, we would probably be in like the $100-something a month range for the storage and the complexity of the real time. The amount of calls we'd be making for the server. Versus if I self-host it, I know how to do port forwarding. I know how to do all the like the program launching and stuff, and I know how to. I have like a UPS at home, so it should be pretty reliable. Yeah. Any questions? Any questions about anything we talked about today? All right. Well, I will be here for another 15 minutes. I think that's all we're going to talk about today, because this is all like code is fun because it's way more complicated than it looks here. But yeah, thank you guys. Thank you guys for coming today. Thank you. If you guys have any questions, send them in the electrical STP chat. I'm going to end the recording here. Thank you guys for attending.